AI Agents 101. Build your own AI agent, a reading companion for people who love rapid development and prototyping. The big idea of this whole story is simple. Open source and commercial tools are now running neck and neck in the same race. You no longer need a big budget or a corporate stack to build something real. You can prototype a working agent today, cheaply and safely on your own machine. Corporate solutions still matter for stability, scale, and redundancy, but the starting line is open to everyone. This document walks slide by slide so you can read it as one continuous journey, from how a model predicts the next word all the way to connecting many agents together. Map of the talk. We open by laying out the full route so nobody gets lost. The talk has 4 sections and 11 topics: how models work, choosing and running them, building one agent and connecting many agents. Think of this as a checklist we keep coming back to. The goal is that by the end you can see the whole picture and know exactly where to start building. Keeping the map visible is itself a prototyping habit. Know your route, then move fast through it. Section 1. How models work and grew. The core of GPT, how a basic model works. Underneath all the hype, a model does 4 things in a row. It breaks text into small pieces called tokens, turns each token into a list of numbers, lets every token look at every other token, and then predicts the most likely next token. Then it repeats. The one thing to remember as a builder is the context window. That window is the only thing the model is aware of, and it has no memory between calls. This is the exact reason we later bolt on memory, tools, and retrieval. Also worth knowing early, the model only ever outputs text, so JSON and Markdown are just text shaped to look structured. What a transformer really is. A transformer is a machine that reads text and guesses the next word, and when you stack many simple layers, the guesses get smart. Picture an assembly line. Each layer is one station that does a small job and passes the work on. GPT-3 stacked 96 of these stations. Depth just means many layers, and the core idea has never really changed. For a builder, this is just the engine you talk to through prompts. Text in, text out, and everything else is wrapped around it. Job 1. Attention. Inside each station, the first job is attention. Every word looks at every other word and asks how much it should care about them. In the sentence about a cat that sat on a mat because it was tired, attention is what links the word it back to cat and not mat. These links are computed fresh for every input, which is what makes the model flexible. Attention is also the expensive part because every word compares against every word, and that is why context windows have a limit and why long prompts cost more. Job 2. The refine step. After the words talk to each other, the second job has each word think on its own. This refine step, also called the feed-forward network, sends each word through its own small network to process what it just learned. A clean way to hold it: attention is words talking, refine is each word thinking alone. Stack 96 of these 2 job stations and you get GPT-3. This refine step matters for the next idea, because it is exactly the part that mixture of experts will replace. How a mixture of experts layer works. Mixture of experts, or MOE, keeps attention exactly the same and only swaps the single refine network for a router plus many small experts. The router acts like a bouncer. For each token it picks just a few experts to switch on, so the model is huge in knowledge but cheap to run. A real example is Q136, which has 35 billion total parameters but only about 3 billion active per token. For prototyping, this is the key trick that lets a near-frontier open model run on a single GPU, which is great for cheap, private, self-hosted agents. Layers, total billions, and the MOE math. There are 2 different dials here. Layers tell you how deep the model is, and parameters tell you the total weight across all stations. They grow at different rates. Depth barely changed in 5 years. The big models today still sit around 60 to 100 layers, close to GPT-3. Size grew by making layers wider and by adding experts. In a dense model, total parameters and active parameters are the same number, so every parameter runs on every token, and a big model is slow. In a MOE model, all experts must fit in memory but only a few fire per token, so active is much smaller than total. That split is why a huge MOE model can run as cheaply as a small one. Talking to a model and the flat text underneath. How we structure a chat changed across 3 eras. Plain text you typed as one block, then clean JSON roles for system, user, and assistant, and finally a tools list the model can ask to call. But here is the demystifier. Whatever neat JSON you send, a chat template flattens it into one plain text string with special marker tokens, and that flat text is all the model ever sees. JSON is for you, the developer. The harness flattens it on the way in and parses the text back to JSON on the way out. This is also why prompt formatting matters so much. Get the template wrong and quality drops even with perfect JSON. Models evolution from chatbots to agents. The timeline runs from 2020 to 2026, completion models that just predict text, then chatbots that follow instructions, then assistants with vision and tools and memory, and now agents that plan and call tools in a loop. The same transformer engine carried us the whole way. What actually changed was scale, training methods, and the shift from answering questions to taking actions. Keep this in mind as encouragement. The engine you are learning is the same one behind every frontier model in the race. Section 2. Choosing and running models. Benchmark map. Benchmarks are just group tests, each measuring a skill like overall knowledge, math and reasoning, coding, or agentic tool use. Each test has a rough score range across today's models, so you know what a good number looks like. The single most useful habit is to stop chasing one global ranking. Pick the benchmark that matches your agent's actual job. If you are building a coding agent, watch SWE Bench and Terminal Bench, not the math scores. Reading a score and trusting your gut. 2 tests up close make scores feel real. SWE Bench Pro hands the model a real GitHub issue and checks if its edits make hidden tests pass. 60 and up means it can fix bugs on its own. Around 30 means a human checks every step. MCP Atlas checks the agent skill directly. Can the model pick the right tool, call it correctly, and chain steps? A smart model can still be clumsy with tools, so for a looping agent this matters more than a math score. The rule of thumb is to trust a clear gap of 10 or more points and treat a 1-point lead as noise. When public tests do not fit, build your own. Your real task is never exactly a benchmark, so make a tiny private test set. Imagine an agent that reads property photos and a listing, then writes a description and a price estimate. Collect 20 to 30 real cases you already know the answers to, write the ideal answer for each, and define a simple score such as a point for the right price, a point per required fact, and a point for inventing nothing. Then run the same prompts through each candidate model and add up the points. The highest score that fits your GPU wins. 20 cases on your own data beat any public leaderboard, and you can rerun the set every time a new model drops. How to read a long model name. Hugging Face names look scary, but they are just labels glued together. Read left to right. Who uploaded it, the base family, the total size, the active size, what it was trained to imitate, and the file format or precision. Useful tags include it for instruction tuned and chat ready, GGUF or FP8 or Q4 for format and precision, CAT for quantization aware training, and distilled for a small model trained to copy a bigger one. For real work, prefer the official instruction tuned build. Treat obliterated or heretic models with care. They have had their safety refusals removed, so they will follow harmful instructions too. Open weight versus closed weight. This is the heart of the whole talk. Open weight models like QN36, Gemma 4, DeepSeek V4, GLM5, 2, and Kimi K2. 6 are files you download and own, giving full privacy, no per token bill, and the freedom to fine-tune and pin a version. Closed-weight models like GPT-5, 5, Claude Opus 4.8, and Sonnet 4.6, and Gemini 3. 1 Pro stay with the lab, so you call an API, pay per token, and your data leaves the machine, usually in exchange for the very newest frontier quality. Neither side is simply better. Many real agents mix both, running a local open model for cheap private steps and a closed frontier model only for the hardest calls. Comparing general smarts. On GPQA Diamond, a hard graduate-level science test, the gap between worlds has nearly closed. Gemini 3.1 Pro, GPT-5, 5, and Claude Opus 4.8 lead near the top, but open models GLM5, 2, and DeepSeek V4 Pro sit only a few points behind. On raw knowledge, the best open and closed models are now within a few points of each other. The separation that still matters for builders shows up in coding and tool use, which is the next chart. Comparing real-world coding. On SWE Bench Pro, fixing real bugs in real repositories, Claude Opus 4.8 still leads at the front, but the striking result is that GLM5, 2, an open model you can download and run yourself, lands above GPT-5, 5 on this test. That is the big shift in the race. A strong coding agent no longer has to be closed. The open frontier is genuinely competitive on the score that matters most for coding. What fits on 132 GB GPU? The rough rule is that the model file must fit in your VRAM with room left for the context. Small and mid-open models fit comfortably at Q4 quantization, Gemma 4 in its 12B and 26B and 31B sizes, and QN3635B which only activates 3B but still has to load whole. The giant open models GLM5, 2 at 756B, DeepSeek V4 Pro at 1. 6T and Kimi K2, 6 at 1, 4T do not fit on a single card and are run in the cloud in practice. Quantization like Q4 shrinks a model to about 4 bits per weight, roughly a 4-fold cut for a small quality loss, which is what makes local prototyping realistic. Flash models trade a little quality for a lot of speed. Almost every lab ships a smaller, faster, cheaper version next to the flagship. The DeepSeek V4 family is a clean example. V4 Pro is the big one. 6T model, while V4 Flash's 284B runs several times faster and costs about 5 times less. Use Flash for high-volume, easy work like classification, routing, quick replies, and first drafts. Use the full model for hard reasoning and final answers. For an agent, this is exactly routing. Send the many easy steps to Flash and only the few hard steps to the big model, an established pattern in real agentic workflows. One model, two flavors, Kimi K2, 6 versus K2, 7 code, both share the same one, 4 trillion parameter base and 256K context. K2, 6 is the general agent for chat, planning, and autonomous background tasks, even large agent swarms. K2. 7 code is a fork built on top of it, tuned for long real-world software tasks with stronger multi-step tool calling, thinking that persists across turns, and about 30% fewer thinking tokens. On coding benchmarks, the numbers move up clearly. The rule of thumb is plain: for a coding agent pick K2, 7 code, and for a general assistant pick K2, 6. What the flagships cost. Using OpenRouter list prices per million tokens, the closed flagships cluster together. GPT-5, 5 around $5 in and 30 out, Opus 4.8 around 5 and 25, Sonnet cheaper at 3 and 15. DeepSeek V4 Pro sits in another league at roughly 44 cents in and 87 cents out, about 30 times cheaper on output while scoring within a point of Opus on SWE Bench Verified. Output tokens are where the cost lives, and agents generate a lot of them in loops. So the cheap money pattern is to route the loop to a cheap model and call the pricey one only for the final answer. Running locally, pick a tool. 4 easy local tools cover most needs. Llama is one terminal command with an OpenAI-compatible API, best for agents and scripts. LM Studio is a friendly GUI to browse, chat, and run a server. Jan and GPT-4 all are dead simple offline apps. And OMLX is a Mac-only MLX server that can run models bigger than RAM alone. All 3 cross-platform tools expose an OpenAI-style API, which is the part that matters for an agent. That means switching between them is a one-line base URL change in your code. For headless agents, Llama is the usual pick, since your code just points at localhost and nothing else changes. The engine that serves the model. One level deeper sits the serving engine. Raw PyTorch or TensorFlow with the Transformers library is the slow research baseline that handles one request at a time. Llama. CPP is the fast C++ engine inside Llama Jan and LM Studio, best for a single user and the only good path on CPU or Apple Silicon, but sequential by default. VLLM is the production server, using page detention and continuous batching to give roughly 3 to 9 times the throughput under load, though it needs an NVIDIA or AMD GPU. The smart pattern is to prototype on Llama and then move the same OpenAI-style calls to VLLM when many agents hit it at once. Will it fit? Check before you download. A model that spills to disk is unusable, so check the fit first. The terminal tool LLMFit reads your RAM, CPU, and GPU, then scores and ranks every model on fit, speed, quality, and context across both Llama and Hugging Face. Even simpler, the Hugging Face model page itself can show a red or green fit mark per quantization once you add your hardware. A 4-bit build needing 151 GB clearly will not fit a single 32 GB card. Checking fit before wiring a model into an agent saves you from a loop where every step swaps to disk and runs painfully slow. Cloud and aggregators skip the hardware. When a model is too big for your GPU, or you just want zero setup, the cloud hosts it. OpenRouter is an aggregator giving one key, hundreds of models from every lab, and automatic routing by price or speed. Llama Cloud runs the same Llama commands on data center GPUs, so you can use trillion-parameter open models, with a free tier and then $20 a month. Azure AI Foundry is the enterprise root with data residency, compliance, and existing Azure billing, and Meta's Llama API hosts Llama models free during preview. For agent builders, OpenRouter is the friendliest, since changing one model string moves your agent to a different model with no other code change. Section 3. Building blocks of an agent. Agent versus just an LLM call. There are 3 levels, not 2. A plain LLM call is one pass, text in and text out, great for summaries and classification but unable to check its own work or fetch anything. A half-agentic loop is a fixed pipeline you write where the model just fills each step. It is cheap and predictable but cannot invent new steps. A full agent loop lets the model decide each step in a think, act, observe cycle until it is done, which is powerful but slower, costlier, and harder to keep on track. The real message for prototyping is to start simple and add loop only when the task truly needs the model to plan and adapt. Most production work is a plain call or a half-agentic pipeline. Structured output, turning loose text into JSON. To get reliable data out of a model, ask it to answer in a fixed shape and then let your code use the result like data. Take a recipe, ask in plain words for strict JSON with a clear shape, get back clean JSON and render it however you like, such as a table of ingredients and a numbered list of steps. Remember, the model still only outputs text, so JSON is just text in a strict shape, nothing magic. The one rule is to always validate. If it does not parse, send it back and ask the model to fix it, and use the model's JSON mode when it has one. Basic agentic loop and when it stops. An agent is a model wrapped in a loop. Think to plan the next step, act to call a tool, observe to read the result, and check whether the goal is done, repeating with new information. This is the RAY-ACT pattern, reason plus act. It can stop 4 ways. The model decides it is finished, a success rule you wrote is met, a safety cap on steps or tokens is hit, or an advanced agent reflects and decides it is good enough. The most important practical habit is to always set a hard cap, because a confused agent without one can loop forever and burn your bill. Tool calling, the 4 shapes. You give the model a list of tools with names, descriptions, and arguments, and it can only ask to call them, never run them itself. The 4 shapes are single, one tool in one pass; parallel, several calls at once run together; loop, tools across many passes; and streaming, partial output shown live for long-running tools. Underneath, every shape is the same 3-message dance. You send the prompt plus tools, the model replies with a structured call request, and you run the function and return the result. That gap where the model only asks and you actually run is your safety control, so always check the arguments before acting. Anatomy of a tool. A tool is just a described function with 4 parts: a short name the model calls, a plain words description, a JSON schema of parameters, and your real execute code that returns a string. On a call, the model picks the tool and fills arguments, you validate them against the schema, you execute safely, and you return a string so the loop continues. A nice framework trick is to keep tools in one internal format and map them to each provider's shape, so you write a tool once and use it with any model. The description is the single most important field because the model decides whether to call a tool from those words alone, so write it like a clear instruction. Inside a real framework, the engine. A framework hides the loop inside one engine that runs the loop, manages memory and session, holds the tool registry, and speaks to any provider through one generic interface. The mental model is a line through the loop. Below it is the LLM, where all the planning and reasoning happen, and above it is the framework, which is pure plumbing that never thinks. A grounding fact is that a basic working agent can be about 61 lines of Python with the whole engine as one class. This engine shape, one loop class owning the registry, memory, and a provider-agnostic model call, sits under almost every framework, so learn the shape, not the brand name. SDKs versus the basic loop. You can handwrite the loop or let a framework handle the plumbing, and each fits a different job. The basic loop is about 120 lines you fully own, best for ad hoc tasks, learning, and tiny agents. Google ADK is Gemini first with built-in tools and tracing. Microsoft's Agent Framework and Semantic Kernel suit Azure and enterprise teams, and LangChain with LangGraph gives a huge library and explicit state loops while staying model agnostic. Pick by the job, handwrite it for a quick one-off, use a vendor SDK when locked to one cloud, and reach for a framework when mixing many models, tools, or complex flows. Frameworks add power and a learning curve, so do not reach for one before you need it, which is the heart of fast prototyping. Memory, Part 1, simple and free first. Since the model forgets between calls, memory is just text you choose to put back in the prompt, and you should start free. Plain markdown files like a notes file are human-readable and Git-friendly, exactly how Claude Code uses its Claude. MD, QMD or front matter adds a small metadata header so you can tag and filter notes, and structured JSON or SQLite lets you look facts up by key. The universal mechanic is always the same. Save a note, pick the few that matter now, and inject them into the next prompt. A single markdown file the agent reads at the start of each run covers most small agents, and you only need a database when notes grow too big to paste in. Memory, Part 2, vectors and embeddings. When notes get big, search by meaning instead of keywords. Embed every note into a vector, store the vectors in a database like Chroma, Qdrant, FAISS, or pgvector, then embed the question and return the nearest notes. You can make vectors with cheap hashing, which catches exact terms but misses meaning, or with a small embedding model like NamicEmbed or BGE that runs locally in Alama, and is the usual choice. The real lesson is that hybrids make an agent smart. Combine vectors with keywords, use tags as a first filter, keep the last few turns plus the top matches, and summarize old notes. Run a small embedding model locally for free and private memory, and only reach for a vector DB past a few hundred notes. Memory Part 3: Reasoning, Memory, and Dreaming. The newest idea is to stop just storing and fetching and instead reason over memory and clean it up offline. Honcho treats memory as a reasoning problem, modeling each user as a peer with preferences and goals, reasoning in the background to resolve contradictions, and answering plain words questions with hybrid search underneath. Dreaming is like sleep for an agent. Between jobs, it reviews past sessions and rewrites its own plaintext memory in light, REM, and deep phases so it wakes up smarter. Crucially, dreaming never touches the model weights, only the readable memory, so a human can approve or undo it. You will not build this on day one, but the direction is clear, and a small model with great memory often beats a big model with none. Same engine, different surface and tools. A fairer way to compare agents is by where they run and which tools ship built-in, not by which is smarter. Code in the terminal means Claude Code, Codex, and OpenCode with file edit, shell tests, and Git built-in. Docs on the desktop means Claude, Cowork, and Hermes, tuned for knowledge work on a folder of documents. Tasks across apps means OpenClaw and Hermes with a real browser, computer use, and chat app tools. Claude Code and Cowork are literally the same engine with different surfaces, which proves it is not about raw intelligence. Match the agent to the surface and the built-in tools, and remember you can always add MCP tools or point any of them at a local model. Coding agents versus general agents. Every one of these is the same think, act, observe loop, so the real difference is the toolbox they ship with. Coding agents come with exact string file edits, compile and read errors, run and fix tests, Git awareness, and repo search, tuned for tight software loops. General agents come with browser automation, chat app connectors, web search, image and text-to-speech, persistent memory, and subagents, making great everyday assistants but weaker at hard multi-step coding. Choosing is mostly about default tools. Need code compiled and tested? Pick a coding agent. Need to drive a browser and post to Slack? Pick a general one, and either can use the model you like. A real agent is not one prompt. A toy agent has one system prompt, but a production agent like Claude Code builds its system prompt from around 20 sections, split into a cacheable static part and a dynamic procession tail to save money. Beyond that, the loop quietly injects hidden messages the user never sees. Per tool rules, recovery nudges when limits are hit, memory and skill attachments, separate prompts for subagents, and context cleanup when the chat gets long. The big lesson is that most of an agent's quality is prompt and context engineering, not the model itself. Clear tool descriptions, good recovery messages, and smart context cleanup are what make the loop reliable, so start simple and add these as you hit real problems. Inside a production loop, one iteration. The clean think, act, observe loop is true, but a real iteration has a lot of housekeeping around it. First, it tidies the context by trimming tool results, snipping old history, microcompacting, and auto-compacting with a summary if needed. Then it calls the model and checks for tool use blocks. If there are none, it runs stop hooks and a budget check before returning the answer. If there are tool calls, it runs them in parallel, collects results, adds memory and skill hints, checks caps, and loops back. The takeaway is that the model call is just one box and the loop is everything that feeds it and follows it. When things go wrong, recovery paths. A real loop plans for failure with concrete side paths. If the context is too long, it drains staged collapse or summarizes old turns and only stops with a clear error if both fail. If it hits the output cap, it retries once with a bigger budget, then injects a resume nudge up to 3 times. If the model itself fails, it catches the error, switches to a backup model and retries. Keep going nudges from hooks or budget checks quietly send the loop around again, and a user pressing stop drains running tools and exits cleanly. Most production failures are these cases, not the model being wrong. So build in a retry, a fallback model, a clean way to handle limits, and an abort path from the very start. Subagents, a loop inside a loop. A parent agent can call a subagent exactly like any other tool, handing it a task in plain words. The subagent runs its own full loop with its own messages and tools, then returns just one clean summary so the parent never sees the mess. The reason is cost and focus. A big task can burn thousands of tokens, so running it in a subagent keeps that noise out of the parent's context. Each subagent gets isolation, scoped tools with a limited blast radius, and guaranteed cleanup of its servers, hooks, shell tasks, and memory. A subagent is simply your agent loop called recursively in its own sandbox, perfect for keeping heavy side quests out of the main context. Section 4: Connecting Agents. MCP, one plug for every tool. Before MCP, every agent wrote its own connector for each tool, and each connector had to know both how to talk to the tool and how to feed results back to the model, so the same glue was rewritten for every framework. MCP, the Model Context Protocol from Anthropic, fixes this. A tool provider builds one MCP server, an agent speaks one MCP client, and they snap together, write once and run everywhere. Architecturally, it looks just like the web, with a host running clients and tool sources running servers talking over JSON-RPC, where each server exposes tools, resources, and prompts. Think of MCP as the vertical layer and the USB-C port for AI. It connects one agent down to its tools and data. How MCP works: a client talks to a server using JSON-RPC. MCP is flexible, but it carries no schema. This is the practical trap people miss. MCP tells the model that a tool exists in the shape of the call, but it carries no meaning about your data. Connect a MongoDB server and the model gets a fine tool, yet it has never seen your collections or field names. So when asked to find active users, it has to guess the collection, the field, and the date format, often writing a confident query that fails silently. MCP will not fill this gap for you, so you add the context yourself. Describe tables and fields in the description or a resource, expose a get schema tool, or wrap a raw find in narrow-named tools like find active users. A bare database MCP is a footgun because meaning is your job, not the protocols. AIAE agents talk to other agents. Where MCP connects an agent down to tools, AIAE from Google, now Linux Foundation project, connects agents sideways to each other, even across companies and frameworks. The standard pattern is an orchestrator that acts for the user and uses AIAE to delegate subtasks to specialist remote agents, while each specialist uses its own MCP tools, with results flowing back through. So the two protocols stack neatly, A2A between agents, MCP from each agent to its tools. The honest advice is to not jump to multi-agent until one agent plus MCP tools is not enough, because A2A adds latency, cost, and new ways to fail. A2A imparts the agent card and the task. Discovery in A2A works like a website. An agent publishes an agent card, a JSON file at a well-known URL that says who it is, what skills it has, and how to authenticate, just like a homepage telling a browser what it offers. Once talking, the objects that flow are a task, a stateful unit of work with an ID you can track, a message for one turn, a part as a content container for text, file, or data, and an artifact as a concrete output like a PDF. It all runs over HTTP with JSON-RPC, supporting request response, streaming, and push notifications. And by 2026, A2A is at version 1.0 under the Linux Foundation with over 150 organizations. Discovery is the real magic. Point your agent at another agent's card, and it can recruit a partner it has never met. UI, the agent sends a UI, not just text. A remote agent cannot touch your screen, so it sends a JSON description of a UI and your front end renders it natively, which is the old server-rendered web pattern reborn. The backend agent decides what to show, for example emitting a flight booking form with a date picker and fields, while the front end in React, Flutter, or Native decides how to show it using its own trusted widgets. The user's click loops back to the agent, which decides the next UI, so it becomes a conversation made of interfaces rather than text. The reason it is JSON and not HTML or code is safety. The agent may be remote and owned by someone else, and sending a described component tree, never executable code, lets your trusted front end render it without running a stranger's code. ATUI versus AGUI, two names people mix up. These are different layers that work together, not competitors. ATUI from Google is a declarative JSON format that describes what the user sees, like the blueprint of a house that says what to build. AGUI from Copilot Kit is an event-based transport stream that carries the live back and forth between any agent backend and any front end, like the postal service that delivers messages but does not design anything. Together, AGUI carries the stream and the ATUI payloads ride inside it, so in a real app you usually use both. The clean one-liner to remember is that ATUI describes the interface and AGUI carries the conversation, and when people say generative UI, they usually mean the ATUI half. Enveloping, passing auth safely down the chain. A single request crosses many hops from UI to backend to agent to another agent, and identity must travel with it, so at every hop the next service must answer who this is and what they may do. The token is the envelope carrying that answer. The trap is authorization creep, lazily forwarding your full powerful token down the whole chain, so a small partner agent ends up holding a key that can do everything, which is dangerous if it is buggy or hostile. The fix is to downscope at each hop, exchanging the broad token for a narrower one scope to just the next step, a pattern called on behalf of, where the new token names both the user and the acting agent for a clean audit trail. The golden rule is to never hand a downstream agent more power than its one task needs. Inside the token, what crosses each hop? A JWT is 3 base 64 parts, a header naming the signing key, a payload of claims, and a signature from the issuer. At each hop, the payload narrows and the actor claim grows. From backend to orchestrator, the token names the user, targets the orchestrator, carries the broad scope the user granted, and names one acting agent. The orchestrator then asks the auth server to exchange it, not forward it. In the new token, the user identity stays the same, but the audience changes to the male agent. The scope shrinks to least privilege, and the actor claim nests to record the whole chain, which is your audit trail. Only the auth server signs tokens. Every agent verifies the signature against the issuer's public key and never mints or edits a token itself, which is what keeps a chain of agents from forging authority. Do not invent your own auth, the standard kit. Rolling your own auth is a classic way to get breached, so use the battle-tested standards. OAuth 2.0 handles authorization, what you may do, and OpenID Connect handles authentication, who you are, the industry default. Because an agent has no human to type a password, the client credentials flow lets it present its client ID in secret to get a short-lived JWT, which can carry the act and on behalf of claims that record who is really acting and for whom. An API gateway then validates every token in one place so each agent stays simple, always granting the minimum scope. 2 extra patterns help. A proxy agent can be the only component holding real API keys so others never touch secrets, and sandboxing runs risky agent code in a locked box to limit damage. What to actually use: JSTS auth and gateways. The practical kit splits into 2 halves and you usually want one from each, all open source and self-hostable, which keeps a safe auth setup cheap for prototypes. In your code, libraries mint and exchange tokens, Better Auth as the default TypeScript auth library, Auth.js for drop-in OAuth and Next. JS Hono for a tiny token exchange endpoint, Keycloak as a self-hosted identity server supporting RFC 8693 token exchange, and OpenAI client with Jose as low-level building blocks. At the edge, open-source gateways validate every token. Kong is the most widely used, Apache API SIX with fully open plugins and high throughput, Tick with a 100% open core, and Treefik as the simplest single binary option. A stack that ships fast is Keycloak issuing and exchanging tokens, your TypeScript doing the OBO swap, and an API SIX or Kong gateway validating the JWT before any agent sees the request, and never handroll the crypto. The whole stack in one picture. This is the payoff that ties every protocol together. Between the user and the agent is 8UI, agent to screen. Below that, an orchestrator uses 8way to talk sideways to your specialist agents and even a partner's agent across an org boundary. Each of those agents uses MCP to reach down to its own tools, whether a database, files, or APIs. Wrapping all of it is enveloping, the identity that travels safely across every arrow, downscoped at each hop, which is not a bolted-on feature but the security that must be present on all the others. 4 protocols, 4 clean jobs. MCP is agent to tools, 8way is agent to agent, 8UI is agent to screen, and enveloping is safe identity across all of it, and you compose them into a modern multi-agent system. Closing and the hands-on workshop. The journey ran from how a model predicts the next token, to choosing and running models, to building a single agent with tools and memory and a loop, and finally to connecting agents together with MCP, 8way, 8UI, and safe auth. The same transformer engine carried us the whole way, and at every step open and commercial tools turned out to be close in the race. Next session is a hands-on workshop where we build an agent together end-to-end. Pick a model, wire a tool, add a little memory, and run the loop, so bring a laptop and an idea. That is the real conclusion of this story. Prototyping a useful agent is now safe, cheap, and open to everyone, with corporate solutions waiting for when you need stability, scale, and redundancy. The one takeaway: the open and commercial worlds are running side by side. You can prototype a real agent today, cheaply and safely, and reach for the corporate stack only when you need stability and redundancy at scale.